Hello, everyone. My name is Alex, and today I'm going to be presenting on Magneto-Hydrodynamics and the sun. Okay, awesome. So I'm going to start by giving a description of the sun and an introduction to Magneto-Hydrodynamics, and then I'll use that as a lens to focus in on various solar phenomena, including sunspots, prominences, and coronal mass ejections / solar flares. So the sun is a big ball of plasma, and it's got 6 distinct zones. The inner core is where nuclear fusion occurs. The radiative zone surrounds it, and it transmits the energy produced by fusion outwards via the absorption of and emission of photons over very long timescales. Surrounding that is the convection zone. It transfers its energy via the motion of the plasma. This is because of the sharp temperature gradient as you go outwards from the center of the sun. Surrounding that is the photosphere. This is what we consider the visible outer layer of the sun. The chromosphere, which is a region of dynamically heating and cooling and accelerating plasma. And the corona, which is a very dim layer that, despite being very hot, is not very dense. So you can't typically see it unless there's something like a solar eclipse. Shown at the bottom of this image are a few different solar phenomena. And I'm just going to read a quote here. All aspects of solar activity owe their existence to the magnetic field and represent different ways in which solar plasma is responding to the underlying magnetic field evolution. So because of the sun's high temperature, all of its constituent atoms are ionized. And so the sun is primarily a conducting fluid. So we can use magnetohydrodynamics, the study of how magnetic fields interact with conducting fluids, to examine the origin of various spectacular phenomena on the surface of the sun. So in 1970, Hans Alfvén was awarded the Nobel Prize in Physics for his seminal work in this field, the basis of which is outlined in his 1943 publication on the existence of electromagnetic hydrodynamic waves. In it, he describes the mutual interaction between electric current and hydrodynamic motion in the presence of a magnetic field, especially the exchange of energy between the electromagnetic field and the kinetic energy of the fluid. He termed this the electromagneto hydrodynamic wave, and the outline of which is described here. So these first 3 equations are Ampere's law, a truncated form of it, Faraday's law of induction, and the Lorentz force law. When you take these 3 equations and you combine them with a hydrodynamic equation of motion, where m is the density, I is the current, v is the velocity of the fluid, and p is the hydrostatic pressure, you can take these 4 equations and, assuming a magnetic field present in a conducting fluid in the z direction, you can describe the evolution of the generated magnetic field in terms of a wave equation shown here. This is a wave propagating in the z direction with velocity v. Alfvén uses this framework to describe the origin of sunspots, which, now that I think about it, I should tell you what sunspots are first, and then we can come back to this. So sunspots, shown in the top left here, are dark features present in the photosphere. Their size is on the order of megameters, so they're very large, and they're cooler than the surrounding environment. In 1908, Hale made the first discovery of magnetic fields outside of Earth, and he did so by observing the emission spectra of the sun and sunspots. So when you look at the emission spectra of the sun and you split it into its components, you'll see essentially all of the visible spectrum with a bunch of dark lines in it. And these dark lines are caused by the absorption of the elemental constituents of the sun, and these occur at very specific wavelengths. What Hale observed was that these lines were splitting into left-handed and right-handed circularly polarized components, and he claimed that this was due to the Zeeman effect. The Zeeman effect is when you take an emitting object and you place it in a very strong magnetic field. If you observe that object's emission spectra from the direction of, or in the direction of that magnetic field, you'll experience the splitting into different circularly polarized components. So that was how he discovered that very strong magnetic fields existed inside of sunspots on the order of kilogauss. So if we go back to Alphen's work, and he was aware of these, of the fact that there were magnetic fields present in sunspots at the time, we can look at this equation for velocity and plug in some numbers. If we assume the velocity of a sunspot to be about 100 centimeters per second, this is guessed from the, or this is estimated from the 11-year solar cycle of the sun, and you take the average magnetic field to be 15 Gauss, that's the ambient magnetic field of the sun. You get this value of 0.002 grams per centimeter cubed for the density, which Alphen stated occurred at about 1/10 beneath 1/10 the solar radius beneath the surface of the sun, placing it squarely in the convection zone, which turned out to be a very good guess. The origin of these sunspots are toroidal magnetic flux tubes that exist in the convection zone. So these are essentially just really big donuts in the convection zone. And these magnetic flux loops experience a buoyancy force. And the reason for that is if you assume that the magnetic flux loops don't experience any horizontal force, you can state that the external pressure is equal to the internal pressure plus a magnetic pressure. The origin of that term I'll get to later. But if you then look at the z-axis, you'll see that the external pressure has to be higher than the internal pressure, and that means that that magnetic flux loop is going to experience an upward force. So sunspots, as you can see in sort of this bottom diagram, are the result of this magnetic flux loop emerging from the surface of the sun, and those emergence points are sunspots. This explains why the magnetic field is directed outward from the sun, and also why it's stronger than the surrounding environment. They also tend to get formed in pairs of opposite polarity because of toroids, when they emerge through a surface, have to have sort of like an emergence and a submerging point. All right, so on to the next phenomena. Prominences are suspended sheets of plasma in the corona. There are two types. There are quiescent prominences, which tend to be larger, last longer, but have lower magnetic fields, and active region prominences formed over active regions with lots of sunspots. Active regions are just areas of emerging flux. They last a shorter amount of time, they're smaller, and they have stronger magnetic fields. The formation of these prominences starts with sort of a bunch of dark strands called fibrils. It's hard to point them out in this image, but they align with each other to form filament channels, which eventually has features like spine, which is the length of the filament, barbs, which are the protrusions that sort of point down towards the sun, and the legs where they touch the surface. Notably, plasma is being exchanged constantly between the surface of the sun and these prominences. This occurs at around 1 to 10 kilometers per second, which is lower than the free fall speed that you would expect on the sun. So there must be some, counterbalancing force to gravity that's keeping this plasma sheet suspended. And this is described using using a prominence sheet model, I believe. So if you take another hydrodynamic equation of motion, assuming that you're in equilibrium, so there's actually no motion, so you set it equal to 0, we have the same terms that we had before of hydrostatic pressure and the Lorentz force, but now we're including a gravitational force in there. And then you also combine that with an expression for the current density and this vector identity. You can get this force balance equation, which splits the Lorentz force component into the magnetic pressure that we saw before and a magnetic tension force. So the hydrostatic pressure and the magnetic pressure counterbalance each other to sort of keep the prominence contained horizontally, but the tension force is what balances out the gravitational force, which causes the prominence to stay suspended for extended periods of time. Okay. So, and then finally, I'm going to talk about the CME and solar flares. Coronal mass ejection is what it sounds like. It's the ejection of plasma and magnetic flux into space. It's described in, there are various ways to describe it, four of which are listed here. The first and the second are just 2D and 3D versions of the same phenomena, which are the eventual instability of these erupting structures leading to recombination. The breakout model is just a numerical model. The emerging flux model is used for modeling very small events. All of these eventually end with something called reconnection, which is the converging of magnetic flux lines and the formation of a current sheet, which eventually gets taller and taller until all the flux and the plasma is ejected from the surface of the sun. Thank you for listening. Are there any questions?